So, continuing with the reliability and testing aspects for the insulation, we have two types of high voltage testing techniques. One is the non-destructive type for particularly for the materials and electrical apparatus, another being the type testing for various equipments. So, the non-destructive testing of materials are basically used to provide the insulation for various electrical apparatus. Insulating materials which are used for the transmission may be of solid like insulators, liquid used for transformer oil, gas may be sulfur hexafluoride in case of SF6 related hardware switchgear, or even a combination of these. These materials should possess good insulating properties over a wide range of operating parameters, namely temperature, frequency, range, etc. The quality of insulation, particularly in any high voltage apparatus, is assessed by measuring the electrical properties like the resistivity, dielectric constant, loss factor or tan delta, partial discharge to detect any deterioration or faults exist in the materials. So, the parameters which could affect the insulation resistance in the are the nature of materials which are being employed for the insulation, the temperature at the operating of the material in the field, any contaminants, the voltage stress or the voltage at which the material is subjected, the voltage stress, the environmental conditions like the humidity, then the frequency of the voltage, applied voltage, whether it is AC or DC, then the time of application of voltage, how long the material has to sustain over a period of application of voltage. So, we have many insulating materials have different have a dielectric constant usually greater than unity and have a dielectric loss when subjected to AC voltages. So, these two quantities particularly depend on the magnitude of voltage stress and the frequency of applied voltage. So, two important factors to be noted here. So, for a capacitor or a cable, the variation of the quantities, the applied frequency and the voltage is of importance. So, if in case considering V being the applied voltage, there will be a charging current, consider here the charging current which is shown here IS, IC charging current IC, and a loss component of the current. The loss component of the current is IL is shown here, IL is a loss component. The total current is given by the charging current plus the loss component, that is I is equal to IC plus IL. The current leads the voltage as you see here, the current leads the voltage by 0 theta, which is less than 90 degrees. Here in case you can see here it is less than 90 degrees. The loss angle that is the delta which is shown here is the difference, that is 90 minus theta. This gives the loss angle for any capacitor having a lossy dielectrics. This is an ideal capacitor. In the ideal capacitor there will be no loss component existing. For a capacitor with a lossy dielectric, this is how a component or a loss component do exist. So, for this you require to measure the capacitance and tan delta of an equipment or a material or for the verification. So, for the capacitance and tan delta measurement, there are several measuring equipments which are being employed. One such equipment being the transformer ratio ohms, So, for higher resolution, particularly for higher resolution, the accuracy, the stability for the capacitance and measurement bridge constructed with transformer ratio arms will provide a very high accuracy. That is one of the reason the transformer ratio arm bridge is used to measure the capacitance and delta. The primary winding, here you have the windings of the transformer, which is shown here. These are the various components, Cn being the standard capacitor, then Cx being the capacitor to be measured, capacitance to be measured. The protection is a fuse unit here, then R and the capacitance which can be tuned or put as a variable capacitor and resistor here. Then we have 3 windings, W1, W2 and W3, Cx being the unknown capacitance, Cn is the standard capacitance, W1, W2 and W3 are the windings of a differential transformer. So, we have a filter plus a transformer here, again a meter which is connected. So, here the primary winding particularly is wound on a toroidal core of high permeability, and also the secondary winding is wound on a core of high permeability. The amplifier, the filter and the null detector, which is shown here, are connected across the bridge. The condition for the balance, that is the null balance, is simply given by the Cx by Cn is equal to Vn by Vx, that is equal to Nn by Nx. So, Cx is nothing but the unknown capacitance of the test sample, Cn is the standard capacitance. So, Vn is the known voltage across that, Vx is the unknown voltage, then N is the winding of the transformer W2 and Nx is the winding side of W1. So, where W1, W2, W3 are the windings of the differential transformer shown here. The null detector is connected with W3 winding, you can see here. So, the MMF in the winding of W1 and W2 oppose each other if current in W1 and W2 are same. So, no voltage will be induced in W3, in case both are same, no voltage will be induced in W3. So, the magnitude balance of the voltage is obtained by varying either W1 and W2, and in case for the phase, to obtain the phase balance, this could be made by varying the variable resistance and variable capacitance which are in the circuit. So, for phase balance, variation of R and C could be used, and for the magnitude balance we could use W1 and W2 windings. So, the test capacitance, that is the capacitance or unknown capacitance which is being connected, which is to be found, can be estimated with a standard capacitor, that is a Cn, into the factor, the multiplication factor, where exactly the multiplying factor for the which is being in the set into the reading, that is the reading where the which you have obtained during the measurement with the adjustments of W1, W2 and R and C. So, these dial readings which are appearing on the transformer ratio bridge will help to get the test capacitance. Similarly, tan delta, the loss factor, could be measured with actual multiplication factor into the reading which is being obtained on the meter after the null detector has been achieved. So, this is how a simple method for measurement of capacitance and tan delta for the equipment is carried out in the laboratories. There are several other bridges which also will help in measuring the capacitance and tan delta. This is again a second type of bridge for like a transformer ratio arm bridge, which is known as a shearing bridge. Here transformer, high voltage transformer, again the test specimen which is to be measured, the capacitance of the is to be measured, and again is connected here, the Cn being the standard capacitor. In here in the present case, the standard capacitor being 68.35 picofarad with a nitrogen filled insulating media. So, this is employed here for the measurement. So, what is initially all the connections are verified, including the battery for the bridge, which is a TETX bridge for measurement. So, we have to energize the transformer using the dimmer stat or a variac in steps and adjust W1 factor. So, where W1 is here, the tan delta factor is here. For the capacitance we have here various readings 100, 10, 1, 0.1 and so on and so forth. So, we have to adjust a factor to least value and have to achieve a null balance in the meter which is being used. So, when capacitance balance is to obtain, then the adjust tan delta value. First initially we have to obtain the capacitance balance, further we do the adjustments for the tan delta. Try to achieve a minimum null deflection. So, that is important with the null detector. The values of capacitance and tan delta could be recorded for various samples or test specimens in the circuit. This is again a simplest bridge which is used in the laboratories for a measurement of capacitance and tan delta. Further, partial discharge measurements, these are very important for the insulation cable insulation and many of the equipments like transformer and so on, where this discharges over in the long period of service could deteriorate the insulation of the equipment or the material. So, it was observed that the dissipation factor or the tan delta loss component is dependent on voltage. So, it became a criteria for monitoring of high voltage insulation. So, taking into consideration the partial discharges are to be measured. So, these what is the partial discharges? So, partial discharges are basically the localized electrical discharges within an insulation system because of the electrical stress and they are restricted to part of a dielectric material. The partial discharges could be classified as the internal discharges. Internal discharges are the discharges which are occurring inside the insulation or the surface discharges. Surface discharges could be on the surface of the insulating material or an equipment, and the third being the corona discharges. So, these are three different types of partial discharges which are classified. So, what are these, how the internal discharges occur? So, internal discharges do occur in particularly in voids or cavities, a small blowholes, or there is a void in an insulation, particularly in solid insulation like the cable or in the transformer. There are small void insulating bubbles where the or because of the insulation on the transformer winding, if there are voids, the discharges could be an internal type of discharges. This could be in solid or liquid dielectrics. So, that is a liquid insulating materials. The surface discharges normally appear at the boundary of different on the surface of any insulating material. So, these discharges could be again degrade the insulation in the period of service. The third being the corona discharges. Corona discharges are related to the gas dielectrics, particularly the gaseous dielectrics, wherever the gaseous media is being used as a insulating medium. So, gas corona discharges do occur. So, these are supposed to be measured and these are to be contained for the better performance of the insulating materials or the equipment. So, the detection of these discharges, internal surface or partial discharge what we call, is based on energy exchange which usually takes place during the discharge, that is namely impulse currents, dielectric loss, electromagnetic radiations, maybe because of the sound, increased gas pressure, or due to the chemical reactions which are happening like in the equipment of a transformer and so on. So, this measurements have to be carried out at regular intervals and to check the healthiness of the equipment which is in service. How partial discharges are estimated or calculated? So, in electrical insulation with any imperfections which is not properly done or has containing voids, this could lead to partial discharges. This is in case of insulating material could be represented by an equivalent circuit, simple equivalent circuit as shown in the figure below here. So, this CC is the CC, CA and CB. CA is the capacitance of the void which is assumed or any imperfections which are existing in the insulating material. CB being the capacitance which is of the remaining series insulation along with CA. Then CC is the remaining discharge free insulation. Like if you consider this, CA is a small void where the capacitance of the void, CB is the total insulation including the void and surrounding, the CC being the series insulation of the material. So, this is represented as a simple equivalent circuit. So, when voltage is applied across the capacitor terminals, a critical value is reached across CA. This small capacitance, the critical value is reached and a discharge occurs in this void or what we call a short circuit, the breakdown of the void take place through the small CA capacitor. So, generally CA, the capacitance of the void is less than the capacitance surrounding the void which is being mentioned as CB, would be less than the capacitance of the entire in series which is available. So, a charge, a small charge, quantum, a very little charge which is accumulated or when discharge happens in the CA, which is known as QA, which was earlier present in CA, flows through CB, that is from the CA it flows through CB, then goes to CC, giving rise to a voltage pulse across CC. When we measure the voltage pulse across, a small pulse is generated which is a small charge emitting from the void termed as capacitance CA. So, a measure of voltage pulse across CC gives amount of discharge quantity which was present in the void, but this measurement is difficult in practice. So, an apparent charge measurement across the detecting impedance is usually conducted in the laboratory, because estimating or directly measuring this it is not an easy task. So, an apparent measurement charge measurement is normally followed in the laboratories to measure the partial discharges. So, how the circuit looks, a partial discharge measurement, there are different partial discharge detectors which are being employed by the utilities or the laboratories where the equipment is being tested or the partial discharge measurements are being carried out. So, for partial discharge measurement you should have a laboratory without any interferences, and the circuit details are shown here for the measurement. You see the transformer, high voltage transformer, you have a filter which is tuned to a particular frequency. Then this is the test sample which is to be measured for the partial discharges. It could be a cable, it could be a transformer, it could be any other material where partial discharge has to be tested. Then you have a calibration capacitor and a calibration pulse arrangement to calibrate the required pulse. Then you have a coupling capacitor at high frequencies. This tries to see the discharges which are coming, which are from the sample could be communicated through the detector impedance, and further from the detector impedance this it is connected to the band pass filter. Again the signal is amplified and it is being monitored in the digital storage oscilloscope finally. So, the filter, a resonant filter prevents, important function of the filter is to prevent any pulses or any discharges generating from the capacitance of the winding for the high voltage winding. These discharges which are energized at that voltage should not communicate, should not pass to the sample. So, that is one of the reason where filter blocks the discharges from the transformer, and it prevents the pulses or discharges going towards the test sample. And also the bushing of the transformer. So, the transformer bushing or the windings could lead to the discharges. This has to be prevented. That is one of the reason where the filter acts as to prevent the discharges further communicating to the sample. The signal developed across the impedance, across this impedance when the measurements is been carried out, this is further passed through the band pass filter amplifier and then displayed on the CO, or a pulse counter, distillation oscilloscope, or a multi-channel analyzer. So, several of these combinations could be used to accurately measure the discharges which are happening on the in the sample which is under test or under measurement. So, that was about the non-destructive type of measurements which are to be carried out for the insulation. We look into the high voltage testing of various apparatus. This is essential as in service an insulation has to withstand, in addition to continuous normal voltages, sometimes higher voltages or over voltages for short durations. So, over voltages of major significance are invariably caused either due to lightning, which could exist for a period of few tens of microseconds higher in magnitude, and it could be seasonal, only monsoon season, so on. And switching operations of the system could lead to switching surges. These switching surges could be of few tens to few hundreds of milliseconds. So, these are the over voltages which are likely to cause the insulation to withstand, or to see that it has to withstand to these surges. So, in addition, apart from this lightning and switching surges, power system could experience the normal power frequency, that is a 50 hertz over voltages marginally above normal maximum voltages. This could be a temporary, and this may be because of dynamic, some problems related to the network, and are also usually not dangerous for a long run. This could exist for few cycles where the voltages could go up. So, also because of deterioration in the insulation. So, not only power frequency lightning switching, it is because the insulation will be continuously in the service. So, this could deteriorate over a period of time, or what we call it as a aging, even under normal working stresses without affecting the lightning or a switching surges. So, under normal working conditions, because aging with time, the insulation could deteriorate and they would degrade the insulation. This could degrade the insulation, where the phenomena like the partial discharges, treeing or tracking could be we could come across such on the insulating materials. This could further lead to the failure of insulation. So, for proper measurements these have to be taken care, and the insulation has to be verified at regular intervals. So, from the above it is clear that a design of any insulation system must be preceded by a critical assessment of likely over voltages, could be lightning, switching, or related power frequency voltages. It has to face in service. This should be confirmed the insulation should be confirmed by proof testing, or some cases a prototype and or full scale model. So, depending upon the confirmation which is to be carried out in any high voltage laboratory under the simulated worst conditions, especially particularly for over voltages, has to be carried out.